Good morning. This is Dr. Kumar Arya, Associate Professor in Department of Chemical Engineering, IIT Jalandhar. Today I am going to explain Newtonian fluid flow in Annulus. So this is the annulus. Here you have the double pipe, one here this pipe and one is the outer pipe. And inside this annulus, the Newtonian fluid is flowing under steady axial laminar flow conditions. So there is no fluid flow in this particular part. Even if there is a fluid flow, but we are not interested to calculate it. We are interested only in this particular segment. This is the side view. This is the inner radius Ri, the outer radius is R0. So this is Z coordinate here along the axis of the pipes. So press P1 at Z equal to 2, Z2 equal to L, press P2. From here we can calculate del P upon del Z is P1 minus P2 upon 0 minus L equal to minus del P upon L. So momentum balance in Z directions in cylindrical coordinate is given by these equations. So here we are putting the constant here. First is steady flow. So this term would get cancelled because nothing is a function of time. Flow in Z direction only. So VR equal to 0 and V theta equal to 0. Del B Z upon del Z term would be equal to 0 if fully developed flow in Z directions. So del B Z upon del Z would be 0 because velocity would not be a function of directions in the direction of flow. Del P upon del Z, this is already being calculated from here. So del P upon del Z is from here. So next is GZ is 0 here because Z is acting, GZ is G cos 90 actually, so this GZ is 0. Now here in this particular part, del BZ upon del R, and then you have del BZ upon del theta and del BZ upon del Z. So del BZ upon del theta, so axisymmetric flow. So this BZ is not function of theta. Now del BZ upon del Z equal to 0 because fully developed flow in direction Z. So by putting all these constants, we will end up with this equation: 0 equal to minus del P upon del Z plus mu 1 upon R del upon del R del BZ upon del R. So we can write from here del P upon del Z equal to mu 1 upon R del upon del R del BZ upon del R. So from here we can convert this partial into total actually. So we go R is the only variable. So if we will integrate that and divide it by mu, we will get one more term here, del BZ upon del R equal to minus delta P upon 4 mu L R plus C1 upon R. We can integrate it again, we will get minus 1 upon 4 mu L delta P R square plus C1 ln R plus C2. This is equation number 1. Now boundary conditions we have at R equal to R0 at the wall of the outer cylinder, BZ equal to 0, no slip conditions. R equal to Ri, BZ equal to 0, no slip conditions because both the pipes are stationary. Substituting these in equation 1, we are getting these two equations. By solving them, we are getting a constant C1 equal to delta P 4 mu L R0 square minus Ri square upon ln R0 upon Ri. Now substituting this into equation number 2, we will get constant C2 equal to delta P upon 4 mu L R0 square minus delta P upon 4 mu L r naught square minus ri square upon ln r naught upon ri ln r naught. Now we can substitute expression of C1 and C2 in equation number 1. So we will get this, we are substituting is, then taking the common, arranging it. So we are ending up with this velocity expression Vz equal to minus delta p upon 4 mu l bracket r square minus r naught square plus r naught square minus ri square bracket close multiply by ln r naught upon r divided by ln r naught upon ri. Now for volumetric flow rate Q, that we can integrate for R actually. So Bz into dA. So this is r dr d theta. So this is differential area. So this is fully filled pipe. So 2 pi, theta is 2 pi, r dr dr. So we can substitute the expression of Vz. So this is the expression of Bz. We are multiplying by 2 pi r dr, integrating it from r1 to r2 or ri to r0. So this is coming here, these terms, so we can integrate it here. So we are taking the hint here, r ln r, we can write integration of r ln r would be from this way, integrating into two parts here. So ln r being considered as first term. So if we solve this here, we are getting this r square by 2 ln r 1 by 4 r square. So this we can substitute directly at this particular place. So we simplify here, so you can substitute this particular term here. So you are ending up with these equations. Now this looks big, we can arrange this is r0, r0 4 by 4, this is r0 4 by 4, this is again r0 square. So this term again will get cancelled, ln 1. So, and this is minus ri 4 upon 4, and this we can write here. So this need lot of arrangement here. So you have all 4 terms here, this is having combined both terms, and this here, this was taken common. So inside bracket is coming r0 square by 4 minus r0 ri square by 2 ln ri upon r0 plus ri square by 4. So this again we can write in this particular format. So again then we can reopen it actually. So if we can reopen here, so you got this term, this side we are multiplying here again, though this is getting cancelled, these two. So finally we are end up here that Q expression is coming with this pi delta p 8 mu l r4 r0 to the power 4 minus ri to the power 4 minus ri square minus r0 square whole square divided by ln r0 upon ri. Now we want to find position of maximum velocity. For maximum velocity the derivative must be 0. So dB upon dr must be 0. So we have, this is the velocity expression, that v equal to minus delta p 4 mu l r square minus r0 square by 2 plus ln ri square minus r0 square upon ln r0 upon ri plus ln r upon r0, differentiating with respect to r here. So this you have minus delta p upon 4 mu l, this will get 2r here. So this you have this particular term, then you are differentiating. Actually, first this you are considering a whole term, differentiating this one only, so you got this. After that you are again because you are differentiating with respect to r, you are getting this term. Arrange them, then we will calculate this. R square is 1 by 2 r naught square minus ri square upon ln r naught upon ri. So r for maximum velocity would be under root of 1 by 2 bracket r naught square minus ri square bracket close divided by ln r naught upon ri. So this shows that maximum velocity will be always closer to the inner surface. Then we can find effective diameters or hydraulic diameters. So that is 4 times of hydraulic the radius. So hydraulic radius is given by cross-sectional area to flow upon wetted perimeters. So cross-sectional area for flow is given by this, pi r naught square minus ri square, wetted perimeter 2 pi r naught plus 2 pi ri. So hydraulic radius comes to be 2 bracket r naught minus ri. So Reynolds number can be calculated. Hydraulic diameter dv rho by mu is less than 2100 for laminar flow. Position of r minimum can be checked by any value. So you can substitute here. This is inner radius, outer radius, and this is the corresponding calculated values for maximum velocity rm. So this all these values shows we are always close to the inner radius in order to find the maximum velocity. So this is all about the flow of Newtonian fluid in the annulus. Thank you.